Okay, so let's jump right in. Our world is constantly moving. It's vibrating, it's humming, it's just buzzing with energy all the time. But what if we could actually capture all that wasted noise and motion and turn it into real, usable electricity? Well, that is exactly what we're going to get into today, the amazing science of harvesting power from the world all around us. I mean, just think about this for a second. Every single time you take a step, you're putting a little bit of energy into the floor. The same thing happens when a truck rumbles over a bridge, or even from the loud noises in a factory. So, the big question is, can we actually grab that energy? Could our own footsteps literally help power the world of tomorrow? Let's find out. All right, here's our game plan. We're going to start with the power hidden in something as simple as a footstep. Then we'll dive into a little crystal physics 101 to see the science that makes it all possible. After that, we'll follow the energy's journey from a raw vibration all the way to a working circuit, look at the big engineering hurdles, and finally, talk about the ultimate test, closing the power loop. Okay, first up, let's just completely reframe how we think about the environment around us. We're surrounded by vibrations, by noise, all the time. But what if all that motion isn't just waste? What if it's actually a massive, untapped resource just waiting for us? You know, every time a car drives by or you walk down the hall, you're introducing what engineers call transient mechanical energy into the world. Just think of them as these tiny little packets of vibrational energy, and we can design systems to actually catch them. This is the raw fuel for our energy harvesting engine. So how on earth do we actually convert that little shake into electricity? Well, the answer is hidden in a really remarkable property of certain materials. So let's get into the core science. The magic word here is piezoelectricity. Now, I know, it sounds super complex, but the idea is actually incredibly simple. There are certain crystals that when you squeeze them or bend them, they generate a voltage. It's a direct one-to-one conversion of mechanical pressure into electricity. And that's the fundamental trick we're going to use. Now, don't let this equation scare you, I promise. It might look a bit intimidating, but it's really just the classic physics of a mass bouncing on a spring. It's how engineers figure out how a harvesting device is going to move and vibrate when it gets hit by a force from the environment. You know, like that footstep. Our whole goal is to make that motion as big as possible. And here is the payoff. That motion, that displacement X we just talked about, is directly tied to the voltage our little crystal spits out. It's that simple. The more you can make the crystal move, the more voltage you get. And that alpha symbol, that's just a measure of how good our crystal is at doing its job. Okay, so we've got a little zap of voltage from a crystal. Great, but what now? How does that tiny electrical spike become useful power that can run something like a sensor? Let's trace the energy's entire journey from beginning to end. It all happens in 5 crucial stages. First, the vibration creates a raw, messy electrical signal. Second, since that signal is all over the place, we have to capture it and clean it up, usually by storing the charge in a capacitor. Third, we regulate that stored energy into a nice, stable power supply. Fourth, we actually use that power to do some useful work, like taking a temperature reading. And then the final and most important stage, the whole system has to do this over and over and over again, completely on its own, powered only by the ambient energy it's collecting. Now, this all sounds pretty fantastic in theory, right? But making it actually work in the real world, well, that's a massive engineering challenge. There are really 4 key areas that researchers are laser focused on to make these systems actually viable. First, you have to tune your harvester so it vibrates perfectly in sync with its environment. Second, real-world noise isn't one clean frequency. It's a messy jumble. So we need special non-linear harvesters to grab energy from that whole spectrum. Third, why not combine different energy sources, like vibrations and airflow? And finally, you have to be an absolute miser with the power you collect, managing every last drop, sometimes at levels below a single microwatt. This quote right here, it really sums up the entire challenge in a nutshell. It's not enough to just make a little power. To have a system that actually works, you have to collect more energy than the system loses or uses just to run itself. It is an incredibly tight budget. And that brings us to the final and honestly the most important concept of all. It's what engineers call closing the power loop. This is the ultimate pass-fail test for any of these energy harvesting systems. The idea is really simple but absolutely critical. The energy you bring in has to be greater than or equal to all the energy that goes out. And that out bucket includes the power for the actual job, plus all the energy you lose along the way. If your input is less than your output, well, your battery is eventually going to drain to zero. The loop is broken. So we can break this ultimate test down into 4 boxes you have to check. Number 1, you have to generate real, repeatable energy, not just some random blips on a screen. 2, you have to be able to tame that raw signal and store it properly. 3, it has to power an actual real-world device. And 4, the big one, you have to prove that your energy budget stays in the black over time. You pass all 4 and boom, you have a truly viable autonomous system. And this isn't just about powering tiny little sensors. This technology has the potential to scale up, way up. A single crystal might only give you microwatts of power, but you bundle a bunch into a resonant module, and now you're talking tens of milliwatts, enough for more complex electronics. But just imagine integrating huge lattices of these things into our floors, our bridges, our buildings. Then we start talking about generating power on the watt scale. The potential here is absolutely enormous.
So, this brings us full circle. We've seen the science, we've gone through the challenges, and we've glimpsed the potential. From self-powered sensors that make our buildings truly smart to infrastructure that can literally monitor its own health, the possibilities are just incredible. The energy is all around us, it's just hidden in the noise of everyday life. So the real question is, what do you think we should power with it?